All right. So let's go.
All of a sudden, what happens is the absorbance at 260 will increase rapidly, just because the aromatic rings of the bases are exposed, because the two DNA strands are separated. So it's hyperchromism. All right. We talked very briefly about replication. We said that in the DNA replication, of course, we need the template, the primer. We need some sort of error repair. We also mentioned that usually we need, of course, your substrates and some sort of divalent ion, such as magnesium or manganese. All right, and the synthesis always happens from 5 to 3. This is, of course, one of the slides we showed for the replication. You have here your DNTP, or the deoxynucleoside triphosphate, being incorporated. And then the phosphate leaves as pyrophosphate, which is later degraded by pyrophosphatase to 2 inorganic phosphates, which is actually the driver of the reaction forward. And then we mentioned, of course, the RNA molecules, which is in itself is very interesting, because RNA molecule, generally speaking, is a single-stranded molecule. It's a single-stranded molecule. And that means it's always like this. And because of the fact that it's single-stranded, sometimes within the molecule itself, bases can find each other. Complementary bases can find each other. They find each other, they have these functional folds. Without those functional folds, the RNA will not be functional, and hence it will not really be useful. And so transfer RNA, for example, the RNA that carries amino acids to the site of protein synthesis, that has to look like this. And you can see that the actual amino acid is hooked up to the 3' end of the molecule, actually to the 2' phosphate hydroxyl. And you can see those various loops. Those loops, of course, are formed because there is no complementation in that loop between amino acids. And those loops are very important. So this whole process is not random at all. Same thing is the ribosomal RNA. The ribosomal RNA has a very complex fold that is extremely important to the function of the ribosome, and hence the protein translation process altogether. Of course, proteins are translated from N to C, from the N terminal to the C terminal. Okay. We also talked about promoters. We just mentioned them very briefly as promoters. And those are regulatory sequences on the DNA that RNA polymerase, the protein or the enzyme that makes RNA, recognizes in order to know where the beginning of the gene is. Okay, and that's what we said about promoters. And transcription termination, we mentioned that too. Transcription termination, of course, is where the RNA polymerase, after it transcribes, it knows where to stop transcription, because it has. Okay. Because we talked about eukaryotes and prokaryotes extremely briefly, as far as the difference between both cells, anatomically speaking. Eukaryotes have a nucleus, and prokaryotes don't. Prokaryotes, of course, are bacteria and archaea. And so we call the transcription with the translation coupled process. Those are coupled, whereas in eukaryotes, they're not coupled. And the reason is the presence of what we call introns, those red things in the immature messenger RNA. Okay, so we have a messenger RNA that is produced from transcription in the eukaryotic part, and that is usually ready, that's not ready for translation. And so we go through a process called splicing in order to get rid of those introns, and then the exons are stitched together to make a functional messenger RNA. In prokaryotes, of course, forget the Shangle Garden, I didn't talk about it, but basically we have the messenger RNA ready immediately for translation, just as it goes out with the ribosome. All right. So we stopped here. We said we're going to, just like we covered in proteins, some techniques of studying proteins in the lab. Yes?
So do you know
They're usually known in trans, at least. Now, that you mentioned that, let me digress a little bit. There are a lot of discoveries that some genes in prokaryotes might carry some sort of intronic sequences. Okay? But that usually is extremely rare and hasn't been found out. But introns / exons, of course, are usually eukaryotic property. All right. So those are some of the techniques that we're going to cover. Basically, I'm also going to go through this briefly, just to give you an idea of what's there. Of course, you are always encouraged to volunteer in one of the labs in life sciences, whether in biochemistry, microbiology, or biology. They have extremely interesting research with extremely capable faculties there. So always, make sure that you keep that as an option, especially if you want to continue this. And of course, we have the other course that covers these techniques in detail, so that's why I don't want to talk about it much. I just want you to be aware of that there are techniques there that we can manipulate DNA on a very molecular level. All right? And those are restriction digestion, blotting, plasmid cloning, PCR, polymerase chain reaction. We can sequence DNA just like we can sequence proteins. And of course, we can synthesize DNA, literally from scratch, we can synthesize DNA. And as a matter of fact, we can synthesize an entire chromosome and make an entire organism. Not that we can create an organism, but we can synthesize chemically the strand and put it in some sort of system that will express it as we would say, genome. All right, so let's talk about restriction enzymes extremely briefly. Restriction enzymes are enzymes actually that exist in nature. Bacteria have those enzymes. Those are basically a very primitive immune system in bacteria. Those restriction enzymes recognize cell DNA, bacterial DNA, from non-cell DNA, invading DNA. Of course, there are invasions and diseases that happen to bacteria, so to speak, which are bacteriophages or bacteriophages, which are basically viruses that infect bacteria and inject their own genetic material. So bacteria can recognize that as a foreign DNA and it can restrict it. Restricting it means cutting it into pieces, rendering it non-functional. And it doesn't do that, of course, with its own DNA because it can recognize its own DNA. So this is restriction enzyme. Many bacteria has it. Many bacteria have it. What they recognize is a sequence we call palindrome. It's another kind of regulatory sequence. Palindrome is an example right there. You can see palindrome down here. Basically, it's a sequence that you can read backwards and forward the same exactly. Sort of like radar. The word radar, you can read it both ways. So if you look at this palindromic sequence, and of course we're talking about 5 to 3 direction only. Right? So if you look at the upper strand from 5 to 3, you see that it's read CC, G, C, G, G. Now if you look at the lower strand, and also you read it from 5 to 3, you see that it's read CC, G, C, G, G. The exact same. Palindromic sequences are distinguished that they have some sort of symmetry in the middle. And then the enzyme, the restriction enzyme, once it recognizes this sequence, what it does is it cuts somewhere along the axis of symmetry. It can cut right at the axis of symmetry, or it can cut somewhere within the recognition basis. In this particular example, it's cutting right around the axis, giving us 2 fragments. Now notice, this fragment has an overhang, has more bases on the upper strand, and of course the other strand will have, the other fragment will have more bases of the lower strand. These are called overhangs. And because they are in the 3' direction, they're called 3' overhangs. Those are also called sticky ends, by the way. The reason they're sticky ends is because if you look at them, they complement each other. They can stick to each other. Okay? That's what restriction enzymes do. And so they recognize that and that foreign DNA, and they immediately cut it this way. And the chances that this particular, for example, sequence is repeated several times throughout the genome is quite good. So really you end up having a fragmented invader, which will not be functional. The question is, would that sequence not be available in the bacteria? I mean, it's really not that unique sequence. The answer is the bacteria probably does have that sequence, But, and I digress here again, bacteria does certain modifications, chemical modifications to their bases, to where the restriction enzyme will not cut it. The foreign invader will not be able to do that. Yes, sir?
You said that that's called a 3' overhang or a 5'?
This is 3', because we're going from 5 to 3, so the last base here is a 3'. Okay. So the overhang is on the 3'. It could be the 5' too, by the way. It could cut, for example, here and here rather than here, depending on the enzyme. Now, those enzymes, by the way, are extremely predictable. And they are engineered. We have them in packages. We can buy them at any time. Okay, here are some of those enzymes. And those are the names of the enzymes. Okay? Banditron, by the way, the names come from the bacteria that harbors that enzyme. Okay? So BAN stands for Bacillus amylo, whatever the other name. Okay? BAN. H1, and 1 is restriction enzyme class 1. We're not going to talk about those. EcoR1 for E. coli. K from Haemophilus egyptius. Okay? Now look at those enzymes, how they digest. Okay? This one, for example, makes a 5' overhang. This one, and you can see they all have axis of symmetry, where the green oval is, and you all can read them, of course, from 5 to 3 and 5 to 3. Okay? That's the thing that they do. All right, so all bacteria have it. Again, you can buy those in order to restrict the DNA route. So those are molecular tools, basically, surgical tools, if you will, for DNA, that we can cut at very specific sites. All right. Electrophoresis, we talked about SDS, electrophoresis in proteins. In DNA, we have also electrophoresis. We can actually use SDS page for electrolyte. We also use more often agarose. It's another material that solidifies into a gel, slab gel. And you can see here in this upper graph, upper drawing, that this agarose slab has usually a well that is casted there. And then you just put it in this reservoir that has a buffer, running buffer. And usually it's under the buffer. Okay? And when you put your DNA is heavy enough, you put enough material that it will simply sink straight to the well. And we call this a submarine gel, obviously because it's submerged. And then, of course, DNA, as we know, is negatively charged because of that sugar phosphate backbone. Phosphate is negatively charged. So it will always run, of course, towards the positive. And just like in page, SDS page, the smaller piece will run faster than the bigger piece. Yeah, same exact principle. And just like in page, we can stain it and see those bands are basically DNA. And again, just like page, we have usually a molecular weight markers that we can use the distance that the DNA travels from here to each one of those bands. Those are some of the markers out there. They usually come in a package with a picture of an agarose gel that tells you the sizes of those. So when you run it, you immediately know that information. All right. Southern blot. We talked about western blot in protein, western. I made a mistake, by the way. I said western is after a person called western, but really it's not after a person at all. Southern is the person that invented southern blot, and his name is Edward Southern, as you can see. All right? And because he invented the southern blot, then when they made a protein blot, they decided to not just because it's southern, they decided to call it western. So based on that, we have actually northern blot and we have eastern blot. Okay? And we have far eastern blots. And those are just named after because Dr. Edward Southern. What did Edward Southern do? He did just like what we described in the proteins. We can do an agarose gel or SDS gel electrophoresis. And the question that we're asking here is whether your fragment, your DNA fragment, is there or not. So the result is, of course, you will take your DNA and you will blot it, again on a nitrocellulose sheet, and then you will have something labeled that only binds to your DNA. Now let me ask you, in protein, southern western blot, what was the thing that binds to the DNA? Was an antibody? Right, it was an antibody, that's right. In DNA, we really don't need antibody because DNA is self-complementary. So if we have it in nature, if we have that other strand that is what we're looking for, that's stable, then we can do simple hybridization and see if our strand can bind to this. So after we run the gel, we denature the DNA. We separate it with single-stranded DNA, and then we have our question single-strand label, and we hybridize it and see if it matches or not. It has some radioactivity or fluorescence. Okay? So Western blot, we usually need antibody. Now, again, just on the side here, tangent, there are antibodies that we can make against DNA sequence. So it's not like it's impossible, but usually in the southern blot, we use the complementary strand. Okay? Complementary strand, western is antibody. All right, so it's the same thing. Before we go there, so this is basically the PCR. Now there are many movies. I'm going to put some, of course, on Facebook, but you also have movies. You can just simply Google or YouTube PCR. You see a lot of that. All right, now let's start our first clicker question. What is a restriction site on a DNA? Okay, so now I need you to identify a palindrome here. As you do so, I want you to remember that it's 5 to 3 has to equal to the other 5 to 3. All right? All right. I'm going to open it. Here we go. Moving on. All right. Typically, what is the temperature profile for PCR? We just talked about this. Right. So let me show you this example. Actually, this is a very cool example. Okay. In human DNA, in our DNA, there are so many repeats like Gaia and like other stuff that just repetitive sequence that doesn't make sense for us, but it has a very important usage. At least the human process system, these are served as fingerprints for our DNA. And if we look at, and those are different lengths, of course. If you look at our chromosomes, at least the FBI decided for now, and they will increase that, all those red markers, A, B, C, D, E, all those are repetitive sequences. Okay? No two individuals on this planet will have all those three identical. And so what they do is they do PCR over those known regions. And then they measure the length of that. And then we can get what we call a DNA fingerprint. And that usually is 100%. All right? So now, what are the possibilities of two people sharing the same A, for example, marker? Why not? Actually, 1 in 10 can share. 1 in 10 can share any of those two together. But if you now take all those 1 to 10 and see how many of those over the 13 markers, we're going to end up having 1 in a 10 trillion chance that this DNA belongs to somebody else other than you. Okay, so that combined 13 markers PCR will give you that possibility. Really, if you have somebody else that looks like this, then you're very unlucky. I suggest you find another planet altogether, much less another planet. All right. So really, the population is about 7 billion. There's only 1 every 10 trillion. So really, it's admissible like this. Here's an example for you. This is an example of a defendant and a victim. Allegedly, the defendant beat the crap out of the victim. And so what happened is this is the defendant DNA, and this is let's assume they're both males, and they did the PCR, and this is their markers, okay? And this is here the victim. Where's the victim? Here's the victim. All right, that's the victim. Now they went to the defendant's shirt and jeans that has splattered with blood from beating that other guy up, and they did PCR on that. And what they found out that the shirt, the defendant's shirt, had the same markers as the victim. So that tells you right away that this DNA belongs to the victim, hence there has to be some sort of things happen there. Okay, so you can see it's a very powerful technique. Of course, it goes beyond that as well. All right, cloning. Cloning is basically having a piece of DNA from one source, one organism, put into another piece of DNA from another organism, having a third organism deal with that, and do other stuff, expressing proteins. For example, the insulin. Okay, we get it. We can clone the gene for the insulin that produces insulin. We can put it, for example, in E. coli bacteria, and have bacteria express it, even though bacteria has no idea what insulin is. It's not in its genetic repertoire, but it can produce it. If we mass produce it very cheaply, then we have to purify that insulin and make actually, for example, something like insulin extremely cheap compared to before getting it actually from the source right away. And this is because we cloned a gene inside E. coli and had E. coli, convinced E. coli somehow to produce it. And that's genetic engineering of cloning. And one of the hallmarks of cloning is the presence of something we call plasmids. Plasmids are basically an autonomous DNA molecule, very small molecules compared to the chromosome. Bacteria, some bacteria have it. And that plasmid usually, in nature, it carries certain advantages for the bacteria if it maintains that value, like antibiotic resistance, the ability to survive under different circumstances of the bacteria because it has those genes. So we were able to identify those plasmids, take them, and engineer it in a way we can put stuff in it. And then put it back into the bacteria, and the bacteria will think that this plasmid is its own, and then it will actually produce the stuff on it, just because it's a plasmid. And so it will make thousands of those plasmids, and then from those plasmids will make thousands of those proteins through the process of translation, transcription translation, and then do what we want. All right, this is a typical plasmid. I really don't want you to know anything about this slide other than this is a typical plasmid. It's a circular piece of DNA that has what we call a reporter gene. A gene that is there that will tell us basically if our cloning is successful or not. Okay? I'm not going to go beyond that. There's a course that covers this. But basically, you have to put it in a plasmid or vector, the piece of DNA that we put it in, and you place it in, and then you have to put it in the appropriate bacteria that will take that plasmid and reproduce the stuff in it. Okay? And what we need here, usually, is a restriction enzyme and something we call ligase. It's another enzyme. Ligase is an enzyme, by the way, that takes two pieces of DNA and stitch them together and make a covalent bond between them, making one whole piece. So if we have two pieces of DNA from different sources, this is our plasmid, and this is our, say, insulin gene, then we can put it together. Notice that they have the same sticky end because they're cut from the same enzyme. And then we put an enzyme ligase that makes it a full circle again. The full circle can go into the bacteria, and the bacteria will be fooled by it, will think that it's on because it has enough of the sequence that is it's original from the bacteria, and then it will just make many colonies and we transfer them. That's all I need you to know about cloning. Restriction digestion, PCRing, ligation, enzyme ligase, and then of course we have to put it in the bacteria. The process of putting it inside the bacteria called transformation. We transform this bacteria with the DNA. Once it's transformed and it takes it, does not always take it, once it takes it, it will then reproduce it. So that means sometimes the bacteria doesn't take it. And that's very possible because that piece of DNA, that foreign piece of DNA that we're putting in the bacteria could be toxic to the bacteria. The bacteria could, for example, doesn't know how to deal with insulin, for example, and then it will kill it, and hence it will not take it. Restriction digest, PCR, ligation, transformation. And of course, then you can do whatever further analysis. That might include protein purification, if you're expressing protein. That might include other stuff we didn't talk about. Okay? Those are the 4 points that we discussed in cloning. Any questions about cloning? All right. All right. Sequencing. DNA sequencing actually is very interesting. I'm going to go very superficially, talking about DNA sequencing. There are so many methods right now, but they mostly right now, they depend on that process of replication. Okay? It's basically the process of replication, but somehow we managed to slow it down in order to read the DNA one piece at a time, one base at a time. Replication usually about 1,000 to 10,000 to 100,000 bases in a second. We managed to slow that down in a very big way so we can read one base at a time. Okay? That's one thing. So usually, the deoxybases, one of the modification to it, we will remove the other OH, make it dideoxy. Now, if you remember DNA polymerase, when it add the next base, it will need that 3' to add the next base. If I remove that OH and makes it making dideoxy, in other words, two atoms don't have that oxygen, then we are terminating the replication. Hence, we're stopping it. Hence, we are slowing it down big time. And that will give us time to read what base was incorporated in that dideoxy. This is one of the principles. And so usually, the bases, we have some humongous modifications on it. See those big modifications? Those are chemicals that emit light when they're hit by something like laser, for example. And so if that is the dideoxy that's added where the termination happens, then we can tell from those different colors which base we add. All right? The result will be these nested fragments where each one will end up with a colorful base, and electrophoresis will resolve. Another way, and really here I just want to know about this, just be aware of it. Really, there will be no particular questions about it. This is, for example, this machine called iron torrent. Again, when we do replication, what do we have? What happens? We have the nucleotides, we have our DNA, we add it to it, and then we have the PPI. And we have an H plus that's produced. H plus, as we know, is basically a drop in the pH by one ion. The iron torrent will be able to read that drop in the pH with every base addition. And so what we're having is something like this. And again, I just want you to have fun here, nothing to memorize. So let me show you the iron torrent. It's basically a pH meter. Each one of those rails have actually its own sensors, pH sensors, and within it you'll have a DNA polymerase, and you'll have the actual DNA strand that we're doing the sequencing on. And so every time it adds a base to it, this is the DNA polymerase, it will produce an H plus that will register on the monitor as one drop because we added A, C, or G, or T. If the base doesn't incorporate for some reason, then what's going to happen? It will just simply go away. You will not have any change in the pH. The machine will know that, and nothing will be registered. If you add two bases, let's say that next sequence is TT, because there's AA on the strand, then you will see a big spike. That's proportional to that. And we'll read it this way. And hence it can sequence automatically. And so if we have thousands of those little pieces, you can imagine we can sequence really tens and thousands of bases of DNA very fast without any problem. Okay, so you can see how the sequencing of DNA is cheap, readily available, and that's why we can do it through that. This is another method also. This is called nanopore. This doesn't rely on DNA replication. This relies on the current, differential current, that's produced because of the passing of a base through this. So we have an enzyme here that makes a hole, like enzymes we talked about, the beta carol that make a hole in their membrane. They have a hole over the artificial membrane, and we have differential electric current here. And then we have our DNA. The DNA will simply be fed through this, and depending on what base is passing through, there's a different electrical signature. That different electrical signature is read and is calibrated to each base, and hence we can sequence something very fast. See here, simply fed through it, that sorts for it, that computer and this is actually the latest. Okay, so that can be fed relatively quickly, and you can read both strands, because both strands are put together at the very end, very difficult. So they will check each strand twice. Okay? So these are the sequencing proteins that are out there. All what I need you to know is that we can sequence DNA based on whatever modifications we did. All right, that's all that we want to talk about for DNA and its techniques. All right, any questions before we move on to hemoglobin? So hemoglobin is another example. We talked about keratin and we talked about collagen, and we've seen how certain sequences can give incredibly amazing structural features for a protein. Now we're going to talk about more of that example. But now we can see as another extreme example here in hemoglobin. Of course, hemoglobin is important for many reasons. It was one of the first proteins crystallized, crystallized. And so we have a structure, the global structure of the protein, like it's all alpha helices that is folded in a bowl, so to speak, right? Right in the middle of it where oxygen is carried, actually right in the periphery, okay? So, and hemoglobin, for the people that study evolution, considered the pivotal point where life went from oxygenless to an oxygen full life, basically, okay, where we started breathing oxygen, and hence we were able to do metabolism more efficiently. Because, as you will see in metabolism, we can metabolize stuff without oxygen and we'll have little energy, while if we metabolize stuff with oxygen, we'll have an amazing amount, abundant energy. And so hemoglobin, of course, is one of the important factors in this. All right. So hemoglobin, of course, carries two things, oxygen and carbon dioxide. It carries oxygen from the lungs to every part of the body, and then it collects carbon dioxide. Actually, it's one of the collectors of carbon dioxide, and it moves it back to the lung where we exhale it. We have another protein called myoglobin. Myoglobin is much smaller. It's a single-stranded protein, and that's specific for the muscles. It carries oxygen to the muscles. And you'll see, we'll talk about a little bit about the difference in the binding profile and how function and sequence actually plays a very important role in having myoglobin where it is and having hemoglobin where it is as far as their specificity. Okay. All right. So hemoglobin has four peptides that are attached together through weak bonds to make a ternary structure, while myoglobin, of course, is only a single one. Let's see here. We will see now, we'll see over the course of this lecture, how oxygen, carbon dioxide, and pH modulate the binding of hemoglobin to oxygen, and how that's very essential for our survival. Okay? So as I mentioned, it's the first protein visualized, and it's the first protein linked to a disease, all right, which is the sickle cell anemia. All right. This is the heart of hemoglobin. It's a non-amino acid molecule. It's called protoporphyrin, or the heme group. Okay? It's basically 4 rings, 5-member rings, that coordinate with an iron in the middle. Those are the 4 rings and iron here. Okay? Now that iron is where oxygen is bound, O2. Okay? The hemoglobin has 4 of those, and so it can carry 4 molecular oxygens. Because it has 4 side chains, right? 4 peptide chains. Myoglobin has 1 of those. Okay? Let's talk a little bit about the structure. This is looking at a cross section at the ring, the hemoglobin ring, the heme ring. And here's the oxygen, the iron. And you see the iron is a little bit sunk under the axis of the hemoglobin. And you can see here we have the histidine. Okay, we have the histidine. This is very important. This histidine binds to the iron, keeping it sunk like this. Once oxygen binds, okay, now this histidine, by the way, happened to be amino acid number 93 on that particular chain. We have 4 chains, so all the histidine in the chains do this. Okay, histidine number 93. Now, when oxygen binds, you see that iron lifts up to the axis of the heme. All right, it hits up, and now we have the oxygen, because the oxygen binds. Now this is very nice. It's very nice. The problem is, oxygen can, if it's not stabilized somehow, can escape, one in a million chance, can escape as a radical, as a free radical, as a superoxide radical. Radicals, they have this extra 1 electron, not pair, 1 electron, that makes them extremely reactive. And reactive, that means they will just try to interact with anything to try to be stabilized. And hence, they will break, the first thing, big molecules, such as DNA and proteins, and hence, it will immediately be toxic. So if that is case as it is, it will be a problem. Okay? So the way the hemoglobin solved this problem, of course, the hemoglobin didn't solve any problem, but the way this thing is designed is to have another histidine that binds to the oxygen on the top. This is called a distal histidine. This is called a distal histidine. This one, this histidine, the one that binds to the iron, called proximal histidine. The distal histidine is histidine number 64. That's the one that binds to the oxygen, and that binding to the oxygen makes it stable. So we would have a 0% chance of having a superoxide ion, radical ion, already having in our cells. Okay, so that's the first thing. Amazing thing structure. See how the amino acids are far away from each other? Because of the folding of the protein. If the protein didn't fold properly, those two amino acids, 96 or 93 and 64, will never meet this way because there's no fold. So folding is very important for structure. All right. So this you need to be aware of those. This is proximal histidine. So in hemoglobin, the 4 chains, 2 of the yes, sir.
Where did the 94 and 60, the 93, 64 come from? Is that the different numbers?
You have the polypeptide chain. If it comes from 1 to the end, if you go to, yeah, that's exactly how the numbers are. So we have 4 of those chains, so hence we have those numbers repeated for that. So it's simply just numbering from N to C. All right, so 2 chains called alpha chains and 2 chains called beta chains. Okay. All right, of course, then again, as I mentioned, myoglobin has 1 of those chains. Now, alpha and beta, they're slightly different. As a matter of fact, beta seems to be the one that's a little modular, and I will talk about this later this class. Okay, that's just a review. The function of distal histidine is what? The function of distal histidine. What does distal histidine do? Now let's talk about the binding profile. Let's look at this curve. This is myoglobin binding to oxygen. By the way, oxygen concentration is estimated usually as a pressure limit. If you have high oxygen pressure, you have a lot of oxygen. If you have a low oxygen pressure, you have less oxygen. So it's sort of like polarity. Okay? So at the lung, we have 100% torus, 100% oxygen. As far away from the lung as possible, we have very close to 0. And here, this y-axis represents the number of myoglobin molecules that are binding to oxygen. All right? So you can see here, as the oxygen pressure increases, as it gets closer to the lung, it almost immediately fills up to where 100% of the myoglobin molecule have the oxygen. And then they will rush, and they will go to where they go, the muscles, and at the muscles, far away from the lungs, the oxygen drops, and it drops, not very rapidly, but you can see just a little drop of oxygen between 25 and 0. Immediately, it dumps its oxygen load. Immediately. So there's no regulation. It picks it, there's no oxygen, it dumps oxygen. There's oxygen, I pick it up, without any thought process at all. No, none of that part is mistake. But basically, that's what myoglobin does. Hemoglobin, on the other hand, has this sigmoidal curve. The sigmoidal from S, sigmoidal curve. That actually is indication of cooperative binding. It's not just a thoughtless binding. That means it can change its binding profile to oxygen depending on the situation. And that's actually extremely controlled, unlike myoglobin. So you can see here that actually, if the oxygen pressure drops to 50%, myoglobin is still holding to most of its oxygen, while hemoglobin already started dumping. If you just extend the vertical line here, you can see that actually about 80% of that, 20% of the hemoglobin dumped its oxygen. Okay? Myoglobin doesn't do that. Myoglobin keeps holding there until it really gets to the absolute minimum. All right? Now, as you drop to 25 or beyond 25, let's say here about maybe 10, you can see most of the myoglobin dumped its oxygen, while hemoglobin is still holding, because it needs to travel further to tissues that are far away from the lung and needs to hold the oxygen more. Myoglobin doesn't need to do that because it works only with the muscles, and hemoglobin compensates. So this binding, this holding to the oxygen and releasing it, not immediately, really is very important for our survival. It's a function. And so we're going to talk about this particular thing. So you can see here, at 25, for example, you can see 50% most of the oxygen is dumped here while hemoglobin is still holding. You can see also that, of course, 100% at the lung. Now, at resting, when we are resting, the myoglobin will not give us any oxygen. Myoglobin will give the oxygen to the muscles and there is some exercise. Okay, but otherwise it's really holding it. Hemoglobin, on the other hand, is still giving the oxygen because tissues do need oxygen at the resting. Now, when you exercise, of course, myoglobin still doesn't give it until we are way low in oxygen, while hemoglobin at that point starts giving that oxygen. And thus I want you to see the difference in the binding profile and releasing profile of oxygen. And we're going to, based on this, we're actually going to be talking about the structure and how hemoglobin does this, while it doesn't. So, the first thing that we want to talk about is that there are two conformations, two quaternary 3D structure conformations for hemoglobin. One is tense and one is relaxed. Relaxed can hold oxygen, bind oxygen very well. Tense, it just simply pops oxygen out of it when it's tense. That's what we call it, tense and relaxed. All right. So here are the structures. The tense are represented as square, and the relaxed as circles. Okay? We have 4 side chains, 2 alphas, 2 betas, so we have 4 places where oxygen binds. And so there are 2 models to explain the binding and the release of oxygen by hemoglobin. One of them is called the concerted model. And this model basically states that hemoglobin, in its 2 conformations, relaxed and tense, they are present at the same time. However, if you look at any snapshot where there is no oxygen, you will see that most of the hemoglobin are in a tense conformation. And hence you can see this equilibrium arrow. The bigger arrow is heading towards the tense and the smaller arrow towards the relaxed. Now as oxygen starts binding around the lung area, then that equilibrium starts to shift. So we have less time now spent at the tense and more time at the relaxed. And that, of course, increases as we occupy the 4 side chains or the 4 active sides of the hemoglobin. This is cooperative binding. Okay? Now we have much less tense. The other model is called the sequential model. That dictates that the binding of oxygen is consequential. Basically, the first oxygen will have a hard time to bind to the tense hemoglobin, but once it binds, it will loosen a little bit the next side and will make the second oxygen easier to bind. Now we have 2 oxygen bound to the hemoglobin. It will make the third and hence the fourth much easier. So there is a sequential event, starting with the hardest one. With it, sort of like your book, your stamp, if you still send mail, but stamp mail. The first stamp is usually harder, but then you can get the next stamp much easier as you peel them off. Okay, those are the 2 models. What other pairs do we have? Now, cells that are actively metabolizing themselves, they actually tend to form many metabolites, and we'll see that in the second part of our course. One of those metabolites is called 2,3-diphosphoglycerate, or 2,3-diphosphoglyceric acid. That's one of the products of actively metabolizing cell. Hemoglobin has a way of actually recognizing this molecule. It recognizes it through a different site. Okay? So we call 2,3-bisphosphoglycerate, or BPG, we call it an effector. It binds to hemoglobin, but not to where oxygen binds. Oxygen binds in those 4 places. There is another site, not the active site of oxygen, that 2,3-bisphosphoglycerate binds. We call this allosteric site. We call this an allosteric site. Allosteric site means the other side. Okay? Allosteric site. It's one word that is separated. Okay? Allosteric site. That's the other side of oxygen, of hemoglobin, that doesn't bind oxygen at all. It has nothing to do with the function of it. 1 or 2,3-BPG can bind to that and can stabilize the square, the tense structure, the one that doesn't like to bind oxygen. If oxygen is bound, I'll go through this so you can read it later. But if oxygen binds to the hemoglobin, it will move from tense to relaxed. Once we have the relaxed conformation, this allosteric site that 2,3-BPG bind to disappears, and hence it cannot bind it. So once we have the site available because the hemoglobin is tense, 2,3-BPG, you can see it here in the middle, binds right here in the hole, right? Once it binds, it forms some sort of hydrogen bonds that will stabilize the tense conformation. So weak bond, hydrogen bond between 2,3-bisphosphoglycerate and those two histidines from the two beta chains, it will form this hydrogen bond that will stabilize the tense conformation, and hence it will stabilize the oxygen release conformation, and it will release oxygen more efficiently. It will not allow it to bind oxygen. Otherwise, if it will allow it to bind oxygen, then it will take oxygen back in the extremities. But this will allow it to release oxygen much better. So this hydrogen bond stabilizes the tense conformation. And the reason is because there's hydrogen bonds between histidines on the beta chain, and those histidines are number 143 that form this hydrogen bond. Once oxygen binds, when we go up there, because the oxygen is overwhelming, this will disappear altogether. And so 2,3-bisphosphoglycerate has no place to bind. The allosteric site doesn't even exist at that point. All right, so let me digress here. Those beta chains, that's part of our normal hemoglobin. The fetus doesn't have a beta chain. It has instead a gamma chain. So it has an alpha and gamma chain. And that's incredible, because oxygen needs to travel even further to the fetus space to deliver oxygen to it. So it needs actually to be in more relaxed conformation longer until it reaches the fetus in order to give the fetus oxygen. If it has the beta, the oxygen will be delivered before the hemoglobin arrives to the fetus. And this is one of the amazing stuff, that we have different copies of this. And we have, instead of beta, we have gamma. And that's going to produce only at the fetus, the fetal level. Once the fetus is out and breathing on his or her own, then we don't need that gamma anymore. We are back to beta. Isn't that amazing? It's amazing. Just because we changed the beta, and because of that, the alpha, the gamma chain don't have those histidines, and we don't have this ability to bind. Because we need to deliver the oxygen to the fetus. Another incredible stuff. Another player, or other players, it's something we call the Bohr effect, after Christian Bohr, the scientist that discovered this or observed this phenomenon. And this phenomenon is very simple. These are the two observations. At low pH, hemoglobin releases oxygen better. That means it's dense at low pH. At acidic pH, at high concentration of hydrogen ion, hemoglobin tends to be tense, and hence it releases oxygen better. At higher pH, hemoglobin will not release oxygen. That's the observation. Why does that happen? Well, there are other things actually here at play that will affect the 3D structure of hemoglobin through weak bonds, one we talked about at the beginning of the semester. So what happened here is we have ionic interactions that are formed, and again, the amino acid is histidine. Now, even though I said you don't have to remember the pKa values, but histidine, we mentioned that it has a pKa value close to the physiological pH, which is around 6, which makes it easily fluctuatable based on the pH changes, as opposed to the other basic amino acids. So what happens here, let me show you that picture in front of you. What happened here is we have the histidine that if the pH is low, if you're at acidic pH, it will be like that, right? It will be positively charged. If we go beyond the pKa, the pH is higher, then we're going to have it as neutral. Okay? This is the trick. This is the trick that allows histidine to do what it does in hemoglobin. So, at pH that is low, since it's positively charged, it will form an ionic interaction with aspartic acid number 94. Now, we don't need to memorize the numbers, just need to be aware of the amino acids. This will allow, again, it's a stabilizing force, just like the hydrogen bonds and the ionic interaction with the DPG. This force also will stabilize the tense and the oxygen releasing conformation. Now, once the pH goes up to above pH 6, then density will be neutral. And when it will be neutral, it's not going to be engaged in the ionic bond with aspartic acid. And hence, we don't have any more of those weak forces, and hence we have more relaxed conformation. So if we have a bond at the lower pH, we have a tense conformation, we release oxygen. If we don't have this bond at higher pH, then we have a relaxed conformation, then to bind oxygen better. You can see again another example of weak bonds controlling the entire process of life, which is the delivery of oxygen. All right? Converts carbon dioxide that's been released in the tissues to HCO3, carbonate, and hydrogen ion. Basically, it's making an acid. It's dropping the pH of the blood. The dropping the pH of the blood will stabilize the tense or the relaxed. The tense. Everything we're talking about stabilizing the tense conformation. The tense conformation is the one that releases oxygen. We will be able to release oxygen at these circumstances. Actively metabolizing cells, low pH, we need to be able to release it because there is active metabolism going, these cells need the oxygen. Okay? And hence they need to bind the carbon dioxide. Finally, carbon dioxide can bind to the amino termini of the hemoglobin to make this charged polar part group that will allow us to actually form further weak bonds to again stabilize the tense conformation. So, in a nutshell, we talked about things that were, time. All right, let's go ahead and stop here. Please don't forget to put your IDs, because that's what I'm going to start adding. And I will see you tomorrow. Now, the quizzes that I'm giving, remember they got extended all the way back to the first lecture. The quizzes are cumulative. Everything we talk about is a fair game. Thank you very much for your time.